Section 4.5 in BC Calc, we're looking at a function x squared all over x plus 1. It's rational, and really just wanted to remind students that when the power above the degree of the numerator is exactly one step higher than the degree of the denominator, that indicates that you will have an oblique asymptote. Technically, we'd have to do long division. At least that's the way we've done it in the past. You could even use synthetic division to help you out. And that's always an option. What I'd like to do, though, is pick back up on the put and take method that we talked about in class before. Take a look at this. This can be so clever. You can say, well, oh, wow, if only we'd have a minus 1. And we could put 1 up there as long as we counterbalance it with a plus 1. Now from here, what you'd see is that you could do a little I heart math. And this would become x squared minus 1 all over x plus 1, plus 1 all over x plus 1. And the whole purpose for doing this is because this numerator now, x squared minus 1, the whole reason that we'd like to see that is that it factors into a difference of squares. You can see very, very nicely that's exactly what you're going to have here. The x plus 1s are going to cancel, and wonderfully and very, very quickly, you now have f of x equals x minus 1 plus 1 all over x plus 1. What this does mean is that right now you know that your oblique asymptote, remember it was always the quotient as you divide. It would be y equals x minus 1. It's a slant asymptote. From the very beginning, you would have noticed that you'd still have a vertical asymptote at x equals negative 1. So we get a large amount of information from this before we even get started doing any particular work. But listen, how about we just continue to do some calculus as well to get a little bit more help in that regard. Let's go ahead and start back up here and say, what if we took a derivative? The derivative of x, of course, is just a 1. The derivative of negative 1, well, that would cancel out to 0. But this thing right here, that 1 over x plus 1, just want to remind you that it's really x plus 1 to the negative 1 power. Taking that derivative, we'd bring the negative 1 down, and then we'd have x plus 1 to the negative 2. So that's how we could take our derivative quickly. And then, of course, this would clean up to look something like this. We could bring that back down. Now, when we're trying to get critical numbers, of course, we've been talking about this all chapter long. If you have a fraction in your derivative, try to unify and get everything to be over one common denominator, meaning, of course, I'm going to multiply the top and the bottom by x plus 1 squared. Right over here, that's why I'm multiplying in the beginning. And then I'd have a common denominator, that's what I'm looking for. And x plus 1 squared is actually x squared plus 2x plus 1. Then we'd have this minus 1 over here. And very, very nicely, very quickly, we could see that the 1 and the minus 1 cancel out. We could actually factor an x from this top to get x plus 2. You can see this is our derivative. This is our derivative. And I'm interested in critical numbers. F prime is undefined whenever we've got a 0 in that denominator. So that's going to be at x equals negative 1. That's a critical number. The top, if you were to set that equal to 0, well, I think you could see we'd have x equals 0. We'd also have x is equal to negative 2. So our critical numbers are going to be negative 1, 0, and negative 2. So what we do and what we've been doing is, as we're searching through this, we can go ahead and make ourselves a little number line and say we've got negative 2 over here, we've got negative 1 over this way, we've got 0. And we're going to do the first derivative test. By the way, definitely want to point out to you our first derivative. You could look at it as this formula right here. You could also look at it as this formula right here. They're one and the same. The only difference is one has a unified denominator and the other one does not. But rest assured, we're going to do some testing, like we could test a 1, maybe test a negative 1/2, maybe test negative 1.5, negative 3/2, 3 over 2, and maybe over here we'll test negative 3. And, no doubt about it, we're just worried about whether we get something positive or negative. Now, when I plug in a 1, again, you could go to this lower section. Every group of parentheses will be positive. That indicates that f is going to be increasing. Your denominator is always positive here. By the way, that's outstanding. You don't even have to check the denominator. But if you were plugging in a negative 1/2 here and here, you can see I'd have a negative 1/2 out in front. Negative 1/2 plus 2 is something positive. It's 1.5. A negative times a positive is something negative. So you can see I'm going to be going down here. How about plugging in a negative 1.5? You can see that this x is going to be something negative. And then the negative 1.5 plus 2 is actually going to be something positive. So you'd have a negative times a positive. That's definitely going to be something negative. We have seen this before where adjoining intervals could both be negative. Plug in a negative 3. The x is a negative and the negative 3 plus 2 is a negative. A negative times a negative is a positive. So what are we seeing? You can more or less see that it sure looks like we're going to have some extrema. It looks like we'd have a maximum at negative 2, at x equals negative 2 when you connect. Looks like we're going to have a minimum at x equals 0. And by the way, if we went back to the original function, and you can see that's up in the top left corner here, if I plugged in f of 0, well, 0 squared all over 0 plus 1, that's a 0. Hey, if I plugged in an f of negative 2, negative 2 squared up here is going to be a positive 4. Negative 2 plus 1 down below is a negative 1. That would get you negative 4. And guys, right now you have so much information about this graph. You really do. Take a look at this again. We'll make a real quick sketch off to the side here. We know that we have a vertical asymptote at x equals negative 1. We knew that from the very beginning. Our function is actually undefined there. We know that we're going to have a slant asymptote at y equals x minus 1. We have a y-intercept at negative 1. We're going to go up 1 and we're going to go right 1. And rest assured, that's going to be our line asymptote that we're going to have here. Now, can keep going. That's negative 2, negative 3. Looks like we're going to have negative 4 down here. I think we're going to need that in just a moment. But look, we're going to have 0, 0 as a point. We're going to have negative 2, comma, negative 4 over here. And rest assured, you can pretty much see what's happening. Your curve around negative 2, it's going to go up, and then it's going to come down. And that's what we're seeing. It's going to be going up, then it's going to be coming down. So, that point, negative 2, comma, negative 4 is going to be a local maximum. Likewise, we knew we were going down, and then we're going to come back up. At 0, 0, you can see just by the number line test, that's where we're going to have a local minimum. And that can help you out tremendously. Okay, we'll move on to our example 3.